Hello, I'm Ananya Kumari of MTech IT 5th semester. Now, in this video, we will be solving the rest of the 4 questions. So, let's start with the first question, which is describe how the coefficients in linear regression are estimated using either the closed form equation or the gradient descendant. So, in linear regression, we actually predict a numerical value by using distance metric that we use to calculate the distance between the observed point and the predicted point. And these coefficients play a very important role in prediction, and estimation of it can be done with the closed form equation or gradient descendant. So let's start. First, we have a linear model, which is y is equal to x beta plus e, where x is the design matrix, beta is the coefficient vector, and e represent both reducible and irreducible error, and y is the output. So in ordinary least square, we minimize the L of beta, which is calculated as the mod of the square of mod of the difference between y and x minus y minus x beta, and the other closed form solution, which is the normal equation, is beta is equal to x to the power t, which is and its transformed form, into x and inverse of it, which is again multiplied by x t and y, assuming that xt and x is invertible. Pros of OLS is it gives exact solution, fast and small medium data sets, and cons of these are computationally and memory expensive for high dimensional dataset and numerical instability when features are multicollinear. While in gradient descendant, it is an iterative method that minimizes the j of beta by 1 by 2n to the product 1 by 2n into the sum of each predicted y minus xi transformed into beta and the square of it, with the update rule in which we have beta tends to be beta minus alpha, and where gradient is calculated by minus of n by n into x transformed into y minus x beta. Variants include batch GD, full data set, stochastic GD, and mini batch GD. It is scalable for large data set and supports multi-streaming and supports streaming data and regularization. Cons of it is that it requires learning rate tuning and convergence monitoring. Solution is approximate, not exact. Like regularization actually modify OLS solution to, here you can see that it has now become x transformed into x plus lambda into I, which is I is the identity matrix, and we calculate then inverse of it, then we multiply it to the transform matrix of x and then to y. And in lasso, which encourages sparsity but has no closed form solution and is solved using convex optimization. Practically, feature scaling improves gradient descendant conversions. Residual and assumptions like linearity, homoscedasticity, and independence should be checked in practice. Moving to the next question, we have explain logistic regression and use logistic function to calculate the probability of a class for a given input example. So here, a logistic regression actually predicts probability of an event, whether it is gonna happen or not gonna happen. Its outcome can be 0 or 1 or true or false. It is binary outcome, just 2. It uses linear combination followed by sigmoid activation. So sigmoid is a function that helps to predict the binary values, which is given here, and the probability of the positive class is computed as this way using base. We don't use base. The probability is calculated this way, and then the output of the model is always between 0 and 1. That represents the probability of the event for if it is going to happen or not. The model is trained using log loss, which is also known as cross entropy, in which we calculate the entropy this way. We first put a minus sign, then we calculate the product of y and log p, then we sum it with 1 minus y and log 1 minus p. Parameters are optimized by maximum likelihood or minimizing negative log likelihood using gradient descendant or Newton's method. So here we have an example in which we are given certain values, and then prediction of the class is when the threshold is 0.5, prediction class is 0. Logistic regression can be extended to multi-class classification using softmax or one versus rest. Regularization can also be used to prevent overfitting. It makes the model simple. Now we have right k-means clustering algorithm discuss how initial centroids influence results. So in k-means clustering, we randomly assign. First, let me explain it in simple words, that we just randomly choose the points, and then we assign the nearby, and it declared it centroid, and then we assign the nearby points to their closest centroid. After that, we calculate the mean of the overall assignment, and then we again assign choose centroids, and then again we assign points nearest to the closest centroid, and we stop when the assignment is said to be unchanged or similar. So it is an unsupervised algorithm, and it can be used for classifying or in categories. Impact of initial centroids: it optimizes a non-convex objective prone to local minimum. Different initial centroids means different final cluster and inertia. Poor initialization may cause empty clusters and slow conversion and suboptimal clustering. And its remedies that we can use for avoiding such situations are that k-means plus plus initialization, probabilistic seeding, which is faster and gives better cluster, multiple runs with different seeds, choose the solution with low inertia, domain knowledge, if we do smarter placement for initial centroid rather than just selecting random centroids. K-means algorithm, which I explained just a few minutes ago, again let's just recall that we first initialize k centroids, and then we assign each point to the nearest centroid, and then we update the centroid at the mean of the points assigned to each circle. Actually, we calculated the mean of the points assigned to each circle. It was my bad thing, sorry. Okay, so we calculate the mean of points assigned to each cluster, and on the basis of that we choose the centroid, and we see if it converges or not, and if it does not change that much, then we stop. Otherwise we repeat assignment. K nearest neighbor algorithm using Euclidean distance. So here we calculate if we need to predict a value, then we calculate k nearest neighbors. And how do we calculate what points are nearest? So here we use descent metric, that is Euclidean. It is used for calculating the distance between 2 points in space. So here we have a training set in which there is xi, yi, where the value of I can go from 1 to n. Then we have a query point x asterisk. Integer k. Here we usually use the value of k to be odd for avoiding ties. For using Euclidean distance, actually the value of k should be 2. Here in the in the distance metric equation, not that k which is chosen. So here you can see that there is a square root, and inside of the square root we have the difference of xi and xj, x asterisk, and the square of this difference, and then the sum of all the data set with it. So here actually we have a point x asterisk, and we are calculating k neighbors. Suppose if we choose k7, so we are calculating the distance of this point with k points using this equation. We calculate the distance of xi point to x asterisk, and then we calculate the square of it, then we calculate the root of it. Compute the distance from query point to every training point sample x, sort all the training samples by increasing distance, and the minimum and the points having minimum difference will be chosen, and then we select k nearest, which is maybe 3, 5 or 7. So we choose 7 points, and then we make predictions. If it is a classification, then suppose if we have chosen 5 points, in which the most frequent class will be chosen for classification, and if it is regression, then we calculate the mean of these 5 points for regression. And it is in this feature scaling is required, normalization, standardization, because Euclidean distance is scale sensitive. Time complexity is OND, where per query n is equal to the training points, d is equal to the features, and it can be accelerated using KD trees or ball trees in low-dimensional data. So if we choose small k, we will face high variance, also called overfitting, and low bias. If we choose large k, then we get high bias, over smoothing. So we use cross validation to select the optimal k. We select certain values of k, then we train our data on, how we train data depends on what kind of cross validation we choose. So suppose if we choose leave one out cross validation, so we leave one data and we train on n-1 data, and we do this for n times. And as for if we have minimum error for a specific value of k, then we choose that value of k. It is a non-parametric and lazy. No explicit training computation happens at query time. So moving to the next question, we have compare decision tree and random forest, boosting, highlighting strength and weakness of each. So all these algorithms are used for classification. The strength of decision tree is that it is interpretable and easy to visualize. We can easily visualize due to its simpler structure, where there is a comparator at each node. It handles numeric and categorical features like data preparation. Little data preparation it requires. And the strength of random foresting, which is also known as ensemble of tree via bagging. In decision tree we just have one tree, but in random foresting we have multiple trees, and we make assumptions or predictions based on the output given by all of those. It reduces variance, it is robust, it is often good out of the box accuracy. Obviously we have multiple decision trees to work together. It handles high dimensional data, rests prone to overfitting, provides feature importance estimates. Talking about boosting, here we build predictive models by sequentially correcting errors. We first make a model. In decision tree we just have one tree. In random foresting we have more than one trees. And in boosting we first have a model that is being trained. It makes mistake, and the next model that is going to be trained will learn from the mistakes of the previous one. So here the performance gets better as models keep developing based on the mistakes done by the previous models. So it really reduces error, and it can handle complex relationship feature interaction. It will obviously perform very better. Weakness, talking about the weakness of all these three, the decision tree is prone to overfitting. It is unstable. Small changes can change the entire tree. Greedy splitting may miss the global optimum. Random foresting is less interpretable than a single tree. Obviously, it will be visually not that much appealing. It requires large memory for many trees. It can be biased for categorical variable with many levels. It is less interpretable. Partial dependence can happen, or shall be used for explanation. In boosting, it is more sensitive to hyperparameters. There are risk of overfitting if it is not regularized. Because suppose if model A has done mistake A, so the next model will train itself based on that mistake, that it will not happen to me. So it risks overfitting. It is slower to train, and it is more complex. The data models train one by one. It is less interpretable. Partial dependence or SHAP is used for explanations. So this is what the strength and weakness of each of these were. Let's move to the next question, which is, so this question is, explain the architecture and components of Hadoop, which includes HDFS, Yarn, MapReduce, or describe Spark and its advantages over MapReduce. So what Hadoop is actually that, if we talk about big data, in this time right now we are generating large amount of data that has to be handled, that has to be stored, that has to be manipulated, but it can't be done on a single system. So Hadoop provides a way of storing this data that comes in great volume, great velocity, and the solution for this is that in Hadoop there is a server containing of nodes that stores these huge data, process it, manipulates it, and gives high throughput. So let's start with the answer. That distributed data processing engine, in memory computation. Actually, this is the review of Spark, in which there happens in memory computation. It supports batch, it supports streaming. In streaming we also needs the process high data processing, high actually processing of data in high volume with high speed. Its main abstraction is RDD, resilient distributed data sets, higher level APIs, data frames, data sets. If we talk about the core components, it has driver, which is used for which is an application coordinator, which runs the main function and create RDD or data frames. And executors, worker process performing task and store data. Cluster manager, which is Yarn, for example Yarn, Mesos, and Sparks. Standalone manager allocates resources, and library is Spark SQL, Spark Streaming, MLib, GraphX. So its advantage over MapReduce is that it performs in memory computation, which is faster. So Spark keeps intermediate data in memory much faster for iterative ML algorithm, and MapReduce, which write disk between each job, so it takes more time. Rich API, data frame or data sets. API make complex operations, optimizations easier. Interactive shell support, unified engines like support batches, streaming, SQL, ML, same framework. Better performance, so it has low latency and better responsiveness. Fewer disk IO operations are required. It is in memory. It performs in memory computation. It is optimized, and Catalyst optimizer for SQL and data frame queries. Tungsten for memory layout optimization. So when MapReduce is still used, so for very large simple batch job on disk when memory resources are limited, but Spark is generally preferred for modern use. Hence we are done with this question. Now let's solve the next, which is obtain basic logic gates from neural networks, summarize them in a table with a number of neurons and activation functions and backpropagation in neural networks, if any. So the logic gates implemented by perceptrons, that is single layer perceptron. NOT gate, single input perceptron with negative weight and threshold. AND gate, in which there are the value of W1 is equal to 1, the value of W2 is equal to 1, and then the bias is minus 1.5, and the activation step, in the activation step the output is 1 only if both the input is 1. Hence since we are using AND gate. In OR gate, the weight is 101, 1 and 1, bias is minus 0.5, and in the activation step the output is 1 if any input is 1. That's what happens in OR gate mostly. NAND or NOR, in this it invert weight and bias of AND or OR. So if it is NAND, then it inverts the weight and bias of AND, and if it is NOR, then it inverts the weight and bias of OR, and it produces NAND NOR. XOR is not linearly separable. It needs multi-layer perceptrons, at least 2 layers. So here in the table you can see in AND the minimum neurons needed is 1, and the architecture is similar perceptron, and the activation step, threshold or sigmoid function, and no training if weight set is manually can be trained via perceptron rule. In OR we have 1 neuron, single perceptron, step or sigmoid, same as AND. In NAND we again have need minimum of 1 neuron, there is single perceptron, the activation function is either step or sigmoid, or the training or backdrops are same. In NOT also we have 1 neuron, single perceptron, step or sigmoid, and then the same happens as AND. In XOR we need more than 1 neuron, and the 2-layer MLP, which is 2 hidden plus 1 output. The sigmoid or TAN or ReLU, and for backdrop it requires training using backpropagation to learn weights. For firstly it forward propagates, then it checks, and then it backpropagates. Backpropagation is used to train multi-layer networks like XOR. If we have multi-layer networks, then we, after forward propagating, we can back propagate to make things correct. Compute gradients of loss with respect to weight via chain rule, update the weights with gradient descendant, and since we can back propagate and analyzing our mistake we can correct it, weights are updated. For single perceptron with activation function, classical perceptron, learning rule is used instead. Differentiable activation enable the backdrop. We are done with this question, and here we have the last question, in which we have to compare CNNs, RNNs, GNs, and transfer learning in terms of architecture and application. So, talking about CNN, the full form is convol- convolutional neural network, and its architecture includes convolutional layer, which are filters, pooling layer, fully connected layer, spatial weight sharing, and local connectivity. It is used in image classification, object detection, segmentation, and video analysis, everything related to, where certain sort of image or scenario has to be analyzed. We need to analyze all the objects there, and all sort of image analysis sort of thing. Its strength is that it is efficient. It have efficient spatial feature extraction and translation and variance. Now, recurrent neural network. Here, its architecture is this way, that the sequential models with the recurrent connections or hidden state, for example, vanilla RN, LSTM, GRU, and it processes sequential data. It is used in language modeling, speech recognition, time series forecasting. Its strength is that it has a model temporal dependency. LSTM, GRU handle long term dependencies. Its limitations are that training issue. There are training issue that in which there is vanishing, exploding gradients in vanilla RNNs, slower due to sequential operation. It is often used for research sort of purpose. Generative adversarial network. Here there are two networks: generator that create samples and the discriminator that distinguish between the real and the fake one. Trained adversely. It's applicable in image synthesis, style transfer, super resolution data augmentation. It produces high quality realistic samples, and but the training instability makes it a little bit challenging. The mode collapse, hyperparameter sensitivity, all these play a crucial role to its performance. Transfer learning, we reuse the pre-trained model, often from large dataset like ImageNet, and fine tune on new target task. It's used in fine tuning CNN for custom image task, using BERT transformer for NLP task. So here we use pre-trained models. For example, in NLP tasks IPS or such as the IPC or BNS problems, here we were using BERT for vector embedding. So here we use one model for more than one purposes. This is called transfer learning. And when label data is limited, we don't have much label data, and pre-trained weights exist. So this was all for the paper. Thank you all for listening to me, and thank you so much.